In this video, what we're going to do is we're going to take our understanding of integration, of the basics of it, and we're going to start to develop it a bit more and look at expanding what we use this on and what we apply it to. Now in this video, we're going to look at solving differential equations. Now to do this, first thing we're going to have to do is understand what a differential equation is, then what types of solution we can get, and then we're going to look at how do we actually get it with a couple of examples. Now a differential equation is quite simply an equation that involves a derivative. So if we look at these ones here, dy by dx equals x squared, that is a differential equation. It's something that links a derivative to an equation form. And the key thing we have to remember with the differential equation is that the solution is an expression for the original function itself. So if we were to take dy by dx equals x squared and solve it and integrate it, we would get y equals x cubed over 3 plus c. This would be the original function. Now, when we are working with differential equations, there's two ways they can be expressed. They can either be expressed as y equals the integral of dy by dx with respect to x, or f of x equals the integral of f dashed of x dx. Both of these have the same meaning. What we're doing is finding the original function based on the way the derivative is and what the derivative is expressed as. Now, as I mentioned, when we solve this, there's two types of solution that we can get when we solve a differential equation. We can either get a general solution or a particular solution. Now, when we solve a differential equation, we get a general solution, we get a family of solutions. And why we get a family of solutions, you ask? Because we're left with a constant of integration. So what we'll end up with is something that's maybe y equals a whole spiel of stuff plus c. So we'll have this plus c as a constant of integration. Now, when I say a family of solutions, you could imagine if we were to sketch these, we would know everything up to the plus c. Now we wouldn't have a value for this. So depending on what value we chose, if we were to sketch these, we would end up with a whole set of functions. We would end up with a whole family of functions drawn because we don't have a single specific value that we're working with. However, a particular solution takes a set of conditions, whether they're initial conditions or something that relates maybe a point of the function, and using that we can actually get a specific value for the constant of integration. So in this case we would only end up with a single answer. So we'd only end up with a single function that we would draw rather than a family of functions. Now, we've looked at what we get when we solve equations with a plus c. That was what we covered in our previous video. What we're going to look at today is how we get this type of answer here, how we get a particular solution. What we have to do with the initial conditions or the conditions that are given to us and how we would use them. Let's imagine we've got the question here. So the graph of y equals f of x passes through the point 3, negative 4. If dy by dx equals x squared minus 5, express y in terms of x. What we want to do is find the particular solution for that, and we know that because we're given this. This is a point where the graph goes through, so this will give us a singular answer rather than a family of curves. Now to solve this, we have to remember that y, our original function, is given by the integral of dy by dx with respect to x. So in this case, it's going to be given by the integral of x squared minus 5 dx. Now, we have to somehow get this into a differentiable form first, but it is already, so we can then just integrate it from there. And again, it's several terms, so it's just a case of integrating every single term, one after the other. So it would be the integral of x squared dx, take away the integral of 5 dx. Integral of x squared, well that gives me x cubed over 3. Integral of 5, so that would be take away 5x because the integral of just a constant gives you a simple x. And we still have to remember and include the plus c. We know that y equals that. Now this is the point where we have to start thinking about getting a particular solution and using this. Because it goes through that point, we know that when x equals 3, y equals negative 4. So what we do with the values now is we substitute these into the equation and we'll find our constant of integration from that. We know then that negative 4 equals 3 cubed over 3, take away 5 times 3 plus c. Well, let's turn that into a simple, nice little linear equation to find c. But negative 4 equals 3 cubed is 27 divided by 3 is 9. take away 15, plus c. So 9 minus 15 gives me negative 6. So c take away 6 gives me negative 4. C equals 2. Now, here's a key point. At this point, do not ever leave it like this. Yes, you've found the constant of integration. Brilliant. But that's not the function. That's not you expressed y in terms of x as the question asks. You now have to explicitly state the full function getting rid of this constant of integration. So you now have to express the full thing as y equals x cubed over 3, take away 5x plus 2. Now you've done it. Now you've expressed y in terms of x, including that constant of integration. Now we're finished. Do not ever forget to do that. You have to include that in there. That could cost you marks if you don't. So that's if it's a y. What happens if it's f and f dashed? Well, same sort of deal really. A function is defined on a suitable domain such that f dashed of x equals x squared plus 1 over x squared plus 2/3. If f of 1 equals x, find f of x in terms of x. Same sort of thing, except this time instead of y's and dy by dx's, it's using f of x and f dashed of x. Same steps though. First step, take our f dashed of x and make sure it's in an integratable form. Well, first term is x squared. That's fine. That's ready. Plus 1 over x squared, well, we have to write that in the form x to the n. Remember, if it's on the bottom, it comes up and it becomes x to the negative 2. We then have plus 2/3. Now, before I go on, one thing I want to point out. X squared and x to the negative 2 are not the same thing. Do not combine these and give yourself 2x squared, or think that they cancel because it's the same numerical value, just positive and a negative, and you're just left with 2/3. Do not do that. They're different things completely. This is like saying an apple plus a banana equals an orange. Doesn't work that way. Leave them alone at this point and just integrate it. We then know that f of x equals the integral of that f dashed of x. So it's the integral of x squared plus x to the negative 2 plus 2/3 dx. So with respect to x. So each term 1 on its own, integral of x squared dx, plus the integral of x to the negative 2 dx, plus 2/3 dx, plus the integral of 2/3 dx. Integrate each of these on their own, so you get x cubed over 3. Well, x to the negative 2 goes up to negative 1, so it's x to the negative 1, and it's then divided by negative 1, plus integral of 2/3 just becomes 2/3 x, and again, plus c, our constant of integration. So now, we just have to sort it and simplify, so negative powers go, sort signs, etc. So we end up getting x cubed over 3, this becomes a minus, and x to the negative 1 becomes 1 over x, plus 2/3 x, plus c, our constant of integration. Now, this is the point where we have to look and say, do we have initial conditions or a condition we can use to find c? Well, yes, we do. We're told f of 1 equals 4. So what that means is when f of x equals 4, we know that x is equal to 1. Substitute them in. We can safely say 4 equals 1 cubed over 3, take away 1 over 1, plus 2/3 times 1, plus c. Simplify it, solve it, you get your value for c. 4 equals, well, 1 cubed over 3 gives you a third, take away 1, plus 2/3, plus c. So 1/3 plus 2/3 is 1, take away 1, that's nothing. C equals 4. And again, great, we've got the value for c. Do not forget to express it in terms of it. Don't just leave it at that point. We want f of x in terms of x, so now we have to say, fine, so f of x equals this function here, but with the c plugged in. So it would be x cubed over 3, take away 1 over x, plus 2/3 x, plus our c, but we know that's 4, so plus 4. So I've done it now at that point. I've expressed it exclusively in terms of x. When solving the differential equations, these are the steps we need to follow, and these are the rules we need to know. If it wants a general solution, we'll end up with a plus c in it, give us a family of answers. If it wants a particular one, there will be some sort of condition in there, whether it's a point the graph crosses, whether it's the value of one thing dependent upon another, whether, for example, like with this one, it's an f of value equals another, it will give you something you can use in order to calculate that c and get your specific answer. But none of the basics of integration change. All our basics rules stay the same, and we still integrate it one term at a time, just like we talked before.